Well, we might have noticed that one thing that we could have done with our limit, with our summations, was that it looked almost as if we came up with a few expressions that could be evaluated for the limit if that number of rectangles increased infinitely. So let's go through an expression where we can actually evaluate one of these limits right here. And the expression that we're dealing with here is the limit as n goes to infinity of the sum from I equals 1 to n of 1 plus I over n squared times 1 over n. What would this look like? Well, in this particular case, when we rework this limit, what we can do is that we can treat it as follows. We're going to take that limit as n goes to infinity of the summation right here that we're going to get from this. Now notice that the summation index is I, so any term that doesn't contain I can be factored out of that limit as a constant. So we're going to have 1 over n times the sum from I equals 1 to n of this quantity 1 plus I over n squared. And if I square that, of course, that is 1 plus 2 over n times I plus 1 over n squared times I squared. And each of these are the kind of terms that we looked at before whenever we were rewriting our summations by using our formulas. So in fact, we're going to be taking this limit as n goes to infinity of the following quantity right here. We're going to have 1 over n times the summation of the constant 1 from I equals 1 to n. So that's going to be times n plus, in this case, we have 2 over n times I. So 2 over n times I is going to become the same thing as 2 over n times, our quantity for I was n times n plus 1 divided by 2 plus, and then we're going to have 1 over n squared, and you'll recall that the quantity for I squared was n times n plus 1 times 2n plus 1 all over 6. Well, clearly this is a quantity that's going to beg for simplification, so we'll do that. We'll note, for instance, that if we simplify it in our middle term right here, n and 2 cancels out, and multiplying 1 over n through to each of the terms gives us 1 over n times n, which is 1, plus 1 over n times n plus 1. And right over here in the last term, n squared and n cancel, leaving us with n right here. We've got n plus 1 times 2n plus 1, which becomes 2n squared plus 3n plus 1. We multiply in 1 over n again, we get 6 over n squared. And so we now have an expression that's a little bit easier to deal with. And we'll take one more stab at simplifying this down, dividing up each of the terms of our fraction so that we can reduce, and then combining our like terms gives us 7 thirds plus 3 over 2n plus 1 over 6n squared. And now if we evaluate this limit as n goes to infinity, we see that we're left with 7 thirds. Well, plus 2 terms that are going to tend towards 0. So overall, we get a limit of 7 thirds. And while this might seem like, well, why would we bother with limits in this case, recall that earlier we were looking at two situations in which we were looking at areas underneath a curve by getting a formula, such as these ones right here, that were going to give us the either inscribed or circumscribed areas of the curve. Well, guess what? If we take this and we work out a limit as n goes to infinity that is increase the number of rectangles underneath our curve of our quantities 8/3 minus 2 over n minus 2 over n squared, sure enough, we find that the area under our curve is 8/3. And so this is actually a really, really useful kind of thing to do.